Assalamu alaikum. Course is Digital Logic Design. Course code is EEE241. This is lecture 2 of week 2. My name is Amna Mehboob. In this lecture, we'll discuss about binary codes and binary logic. In binary codes, we'll discuss about BCD, gray codes, and some other codes. Binary logic, we'll see what a binary logic is, logic gates, what are the notations of logic gates, what are the symbols of logic gate, and the truth tables of these gates. Starting from binary codes, first of all, we should know why we use binary codes. Because the digital systems, they don't only represent numbers, that is decimal numbers, that is 0 to 9, but they represent or manipulate many other things, many other discrete elements of information. And these discrete elements are represented with n bits of binary codes. So there are many codes which are used, that is BCD code, gray code, ASCII codes, and etc. For example, if we talk about binary coded decimal, that is BCD code. BCD code is that for example, if we have 185, its binary will be 1011001. We use binary codes also, binary numbers also, but sometimes, or most of the times, we have to represent different things. For example, if I talk about alphabets, each alphabet is represented by a different code, that is ASCII codes. And similarly, BCD codes means that, for example, if we talk about 185, we will not represent it in this way. That is, we'll use 7 bits of bits and have converted 185 to binary. Instead, in BCD, each digit represents a different number, and we represent one. Each digit is represented by 4 bits, and 185 is considered as 3 different digits. So for 1, we'll have a combination here. For 8, we'll have a different combination, and for 5, we'll have a different combination. So this 3-digit number is represented by 12 bits, but every digit is represented differently and can be handled differently. This table here represents the BCD digits or the BCD code. In this table, we can see that decimal symbols are represented, the BCD digits, a BCD combination, BCD code of different decimal numbers are represented here in this table. Decimal digits starts from 0 till 9. So in BCD, we have given all these 10 combinations a 4-bit code. For 0, it's all zeros. For 1, it is 001. For 2, it's 0010. It's basically a binary of all these numbers, individual numbers, represented in 4 bits. Why we need 4 bits? Because we have to represent, or we are representing from 0 till 9. So 9 is represented, 8 and 9 are represented in 4 bits. Now the second question is that we are using 4 bits, and we all know that by 4-bit we can represent 2 raised to power 4, 16 combinations, but here we are using only 10 combinations. The rest of the 6 combinations are unused. We don't use them in BCD codes. And in further, when we study different chapters, we'll see what unused codes are and what we do with them. Now comes BCD addition. In BCD addition, the main concept of addition or binary is the same as binary sum, but the difference here is that, as I said before, that we represent 0 till 9 digits are represented in BCD. So if we have a number that is greater than 9, for example 10, then it is represented, or it is considered as 2 different digits, and one will be represented with its BCD. So 10 is represented as is considered as 2 different digits. For 1 we'll use 0001, and for 0 we'll use 4 zeros. So to cater this problem, what we do, if we have a sum that is greater than 9, that is 1010, we add 6 to it so that we can represent it in we add a 6 so that it can be presented in a proper way or in a correct digits, and we'll see how it is happening, and then I can explain better. For example, if we have 4 and a 5, and we know 4 plus 5 is 9, so no problem in it because 9 has a distinct BCD code for it, and we have for 4 the BCD code is 0100, for 5 it is 0101. We add it, we get 1 0 0 1 and 1001 9. Now let's come to 4 plus 8, that is 12. Now 12 is greater than 9. What we do? First we'll take a BCD code of 4, then we'll take a BCD code of 8. We add it, we get 1100, which is greater than 1010. So what we'll do, we'll add a 6 to it. Now when we add a 6 to it, the answer becomes 010101. Now if you see, these 4 bits represent 2, and this one, when combined, we'll get we'll add 3 zeros to it. Again, by adding 3 zeros to its most significant bit side, doesn't change the magnitude of that number, and this is 1. So our answer is 12. So basically, when we get a number greater than 10, it is in binary. This is 1100, that is binary. But in BCD, we can't represent 12 with its binary. We have to convert it into BCD codes. Now again, let's see another example, that is 8 plus 9. Again, we'll take BCD of 8 and 9 and then add it. Now the answer is 10001. This is binary of 17. But as I mentioned before, that in BCD code we don't take binary. In fact, 17 is considered as 2 different digits, and it should be written as BCD of 1, that is 1, and then we should have a 0, that is 7, that is 0111. So this binary of 17, if we add in it 6, that is 0110, and we get this. These first 4 bits are 7, and then we have a 1. We add 3 zeros to it, and we get binary of 17. So whenever we have a BCD addition, the process is the same, but there are 2 differences. First of all, it's BCD, so every digit is considered as a different entity or an element or discrete elements. So we add differently. And then secondly, if we get a sum that is equivalent is greater than 9, or I should say it's equivalent to 10 or more than 10, we add 6 to it, and by adding the 6, we get the correct digits to it. Now let's just take an example that in which 184 is added to 576. A 3 digits number is added to a 3 digit number. First of all, 184 will take a BCD of 1, BCD of 8 and a BCD of 4. 576 will take BCD of 5, BCD of 7 and BCD of 6. Then we'll add digits individually. So 4 is added to 6. You will see that this process is exactly same as we do in a decimal addition. The difference is that instead of 184 or decimal digits, we are representing it in binary numbers. So the whole process is the same. We'll add 4 and 6, that is 0100, 0110. We get 1010, which is greater than 9. So we'll add a 6 to it, and the answer is 0. 1 will add become 0, and 1 will have a carry here. And then we'll have a 0, and we have a carry here, and then 0. Now again we have a carry 1, which will go to here. Now we'll add this 8 and 7 and we have a carry 1, so we'll have 0. Again we'll have a carry here, then we'll add 1, we'll have 0 and 1, 0 and 1 and 0 1. Now again this number is greater than 9, so we'll add a 6 to it, and we'll have 0 1 1 0, and this one will become a carry to the next digits, and that is 1 and 5. Now these three ones will add become 1, and then we'll have a carry here, then we'll have 1 1 and 0. Now this number is not greater than 6, so we will not add this number is not greater than 9, so we'll not add the 6 and this. Now if you see, okay, 184 when added to 576, we all know that this is 0, then we'll have a carry here. 8 plus 7 is 15, plus 1 16, 6 and a carry here, and that is 760. And here in BCD 0111 is 7, 0110 is 6, and these are 0. So this is the way how we add in BCD. Now we have when we talk about addition, we need subtraction also. So in decimal arithmetic, the subtraction process is the same. In that, what we do is that 375 we'll take BCD of it. When we want to subtract 240 from it, we'll take 240 9's complement of 240, and 9's complement of 240 is that if we have a 240 here, we'll subtract this 240 from 3999, and in this case we'll have 9, 5 and 7, and then we'll have a 1, and because we are doing 10's complement, 0 1 6 7, and because it's a negative number, we are doing signs complement, so we'll take another bit here which will sign bit, that is and sign bit, that is 9. So we have 9760, that's 10's complement of this number, and then we'll add it, and when we add this, it will get 5, 7 6 is 13, 3 1 1 is carry here, 7 3 is 10, plus 1 11, 1 here and 1 carry, and 9 plus 1 is 0, and we have a carry, so which indicates that the number which we have is a positive number, and that is 135. And the process, when we'll do it in BCD, we'll do exactly same as we did in the last slide, that we'll convert, or we'll take BCD of 3 7 and 5 and 9 7 6 0, then we'll add, and if the sum is greater than 9, we'll add 6 to it, and we'll complete the process. Now there are some other decimal code which are widely used or were used before, and we get new codes, but mostly the most commonly used are the BCDs. Here we have BCD, and the weightage of every bit in the BCD is that the least significant bit has a weightage of 1, then 2, 4 and 8. It's the same as binary, that is 2 raised to the power 0, 2 raised to the power 1, 2 raised to the power 2 and 2 raised to the power 3. Then we have 2421. This 2421 basically means that 2421 are the weightages given to the bits. Starting from the least significant, the first bit has a weightage of 1, second bit has a weightage of 2, third bit has a weightage of 4, and fourth has a weightage of 2. Excess 3. Excess 3 is that we add 3 to the BCD of any decimal number, or I should say that we add 3 to the binary of the respective number. For example, if I talk about 0, I'll take binary, 4-bit binary of 0, and then add 3 to it, and in this form we get excess 3. Then we have 8 4 minus 2 minus 1. Again, these are the weightages given to the bits. The first, starting from the least significant bit, its weightage is minus 1, second minus 2, 4 and 8. Now and here you can see under this line, these are the bits in every case, in every code, which are not used, are the unused combination. Again, why are these unused combination? It's because all these codes use 4 bits, and they have to use 4 bits to represent 9, because we have 10 combinations, and 10 combinations mean that we need more than 3 bits. So we use 4 bits, and 4 bits means that the total number of combinations we get are 16, but to represent 0 till 9 we need 10. So 6 combinations are unused bits in all the codes, but the unused bits are different for every code. Like for BCD, these are the unused, which for example 1010 and on. In 2421 there are some other 6 bits that are unused. Again XS3 has some other, and 84 minus 2 minus 1. So if we talk about each and every code, so BCD we already saw that it's very simple, that we take the binary of every decimal digit. 2421 is, as I said before, that these are the weightage. So for example, if I want to write a 0, I don't have to give any weightage to any bit, so I write 00 to all. 1 can be written as the 0001. Now for 2 can be written as 0100, also 1000, because we have 2 bits that has weightage of 2. Okay, and 3 I can write as 0011, so I give weightage to 1 and 2 here, or I can write 1001. 1001, again this will have a weightage of 2, and the last one will have a weightage of 1, has 3. So in 2421 some of the digits can have more than one combination, but we always use 1, and the other combination we say is unused. Like for if 2 I am using 0010, then 1000 is unused combination. We can't use this combination for other digits. Similarly for 30011, if I am using, I can't use 1001 here. It is now unused. So we can have different combination for some digits, but we always have to choose 1, and the other is in unused. XS3, as I said before, the digits we want to represent, we take its binary, and after taking the binary we add 3 to it, and these are the combinations. And so because we add 3 to it so 0, 1 and 2, we will not see a 0, 1 and 2, these are unused. And then because 9 is represented by adding 3 to it, that is 12, so 13, 14 and 15, they are also unused. 84 minus 2 minus 1, this is a unique code because it is using a negative weightage and a positive weightage. So if I talk about 0, it's all zeros. If I talk about 1, it's not set that straightforward. I don't want 8, I will have a weightage of 4, minus 2 and minus 1. So 4 minus 2 will be 2, and then minus 1 will be 1. That's why my code is 0111. Now if I talk about 2, again it's not that straightforward. I have to use some different combination here. So if I use give a weightage 1 to 4 and a 2 minus 2 weightage, the 4 minus 2 is 2, so that is why 0110. In this way we have these codes, and these are the unused codes. Now 2421 and XS3 are called self-complementary codes. Self-complementary codes means that if I write a 9's complement of the decimal number obtained by any of these codes, their complement is very simple, and the complement is that I only have to flip the bits. For example, if I talk about 395, if I write 395 in XS3, my 3 is 0110, 9 is 1100, and 5 is 1000. So this is 395 in XS3. Now 395, its 9's complement is 604. You can again calculate it by subtracting 395 from 999, and 604 I can obtain by flipping these bits. That is, if I have 0110, I'll make it 1001. 1100 is 0011, and 1000 is 0111. Now if you see 1001 here, is for 6. 0011 0011 is for 0, and 0111 is, here it is for 4. So how I got 9's complement of XS3 code, that whatever digit I was given or number I was given, decimal number, I took its XS3 and just flip or change the XS3 code by replacing 0 with 1 and 1 with 0. The result which I get is basically 9's complement of 395. BCD are not self-complementary. And as I said before, 84 minus 2 minus 1 code is a different code, because it gives positive as well as negative weightages to decimal codes. Each code has some benefits and some advantages and some disadvantages. XS3 were used before because of their self-complementary nature, and some codes are not being used now, some are using. Gray code. Another way of writing the BCD, decimal numbers. In fact, gray code is not limited to related to BCD. It's a way to write any number. First, when we initially 0 was given all zeros, then 1, 001, and then comes 2, and we used to write 0010. Now if you see 1 and 2 here, double zeros are same, then we have a 0 which is changed to 1, and then we have a 1, it's changed to 0. So from 1 to 2 transition, we need 2 bits to change. Similarly, other bits were also the same. So binary code says that, or I should say the advantage of the gray code is that when we have a binary code sequence, when we move from one sequence to another sequence, only one bit in the code changes. Like for 1, if we have 0001, so to write 2, we will not change 1, we'll keep it the same, so that only one bit changes. If I change this 1, it will become 0 and it will be 0. So I will not change this 1. The next bit is 0, I will change it 1, and the rest 2 bits I'll keep them same. So I have changed only one bit. Now let's come to from 2 to 3. 2 is 0011. Now if I want to change from 2 to 3, I'll again check here, and this one I'll change it to 0, and the rest 3 bits will be the same. In this way, from 2 when moving from 2 to 3, only one bit changed. This gray code we'll see in a 3rd chapter or 4th chapter in Karnoff map, K-map. These gray codes are widely used there. Now comes binary logic. The second part of this lecture was binary logic. In binary logic, we'll see, or we'll discuss about 3 important operations that are used in binary logic. First is AND, another is OR, and third is NOT. When we talk about AND operation, AND means that if we have 2 things, and for example I say X and Y, it means both of them are required. It's not possible that if one thing is there and the another thing is not there. We need both the things. So AND operation says that X dot Y is equal to Z, or X multiplied by Y is equal to Z. We've used both these notations, this a dot, and if we don't use any notation as we use in mathematics for multiplication, both these notations means that we are doing and the output Z will be 1 if and if only both of these inputs are 1, are available, are 1. If any one of the bits are 0, then the other the output would be 0. OR operations mean, as we say, if I say X or Y, it means that I want any one of them. If only one of them is available, it's good, and if both of them are available, again it's good. So x and or is the notation for or is plus sign. So x plus y is equal to z, means that z will be 1 if any one of these inputs are 1 or both of them are 1. But if both of them are 0, then output will be 0. Not, it's a negation, and negation means that if x is 0, the output will be 1, and if x is 1 or the input is 1, output would be 0. So x bar is equal to z, or it's a complement operation. And before moving to the next slide, we should not get confused by the sign multiplication and plus with decimal multiplication and decimal plus. The decimal multiplication or decimal number multiplication, decimal number addition are different from these. They are logic operations, whereas those are decimal operations, arithmetical operations. Now here you can see a truth table. Well, truth table basically is that whatever operation we are performing or logical operations we are using, we can represent it in a truth table. Truth table is a table in which we give output or of all the possible combinations of input. For example, if I say about AND gate, we have two inputs x and y, and if two inputs, total number of combinations are 4. So in a truth table we'll give all the combinations for our 2-bit inputs or 2 inputs and see what are the outputs for all these combinations. So x and y can be both of them can be 0, x or y, any one of them can be 0 and other can be 1, and lastly is that both of them are 1. So if both of them are 0, output will be 0. If any one of them is 0, output will be again be 0, and if both of them are 1, then our output will be 1. Same truth table, in the similar manner we can have a truth table for OR gate and OR operation, and again x or y are 2 inputs. We'll have 4 combinations, and for each combination we'll say the output. If both of them are 0, the output will be 0. If any one of them is 1, our output will be 1. If of both of them are 1, then also our output will be 1. Then is NOT gate. NOT gate is with one input x, and x bar is its output. Its complements, its negation or invert. So if its input is 0, input, because we have 1-bit input, or total combinations are 2. So if its input is 0, output will be 1. If input is 1, the output will be 0. Now, when we talk about our digital systems, our computers, we have our electronic circuits, we have logic gates in it. Logic gates are AND, OR, NOR, NAND, and others. And basic are AND, OR, and NOT, which we just saw, and we'll see their symbols in the next slide. But these logic gates operate, or the input to these, or the signals to these, input signal to these logic gates basically are voltages and current. Depending on the voltage or current received as an input to these gates, we get output. So if our voltage are from 0 till 4, so depending on the technology, we have our logics. If, for example, we have a 0 to 4, we can say that from 0 to 1 voltage, the range of voltage or the current will be logic 0. That is, from 0 to 1 voltage, we'll consider it is as logic 0. From 3 to 4 volts, we'll say that it is logic 1. If a signal's voltage lie between 3 and 4, we'll say it's logic 1. If it's between 1 and 3, it's a transition. We will not say it's logic 0 or logic 1, but it is transition in transit. It is transit, or it is moving from 0 to 1 or 1 to 0. These are the symbols used for AND gate, OR gate, and NOT inverter gates. So, and these are widely used gates symbols. we have a straight line and a D shape of gate for AND. We have a curve here for OR, and we have a triangle with a knot. This knot indicates invert. If we don't have this knot here, bubble here, then it's a buffer. It means that if we give X input, then we'll get an X output. But this bubble basically is the inverter with this triangle. One important thing is that when we talk about the logic gates and discrete systems and electronic circuits, is timing diagram. To present our input output, we show a timing diagrams. Timing diagrams basically is that we'll have inputs and our respective outputs, and we can show our inputs with help of these graphs. Lower level means it's a 0, upper level means a higher level means that it's 1. So for example, if X and Y, both of them are 0, we have a value, and this here both of them are 0, the end will be 0. Both of them are 0, then our Y OR gate output will also be 0. And this third output is not of X, that is complement of X, and X is 0, and its complement will be 1. Then next here we have X is 1, Y is 0. So if X is 1 and Y is 0, AND will be 0, OR will be 1, and NOT will be 0. In this way, and again let's see here, X is 1 and Y is also a higher level, means both of them are 1. So AND will also be 1, OR will also be 1, result output of OR gate. NOT will be 0. Then we have a 0 and 1. Again one of them is 0, means AND is 0, but OR gate is 1, and because we are taking complement of X, it is 1. In this way we can write a timing diagram of any gate or a circuit given to us, in which first we represent our inputs, and lower level means 0, higher level means 1, and then we represent our outputs depending on these inputs. Our gates can have multiple inputs. Till now we saw that our gates have 2 inputs, X and Y, but we can have multiple inputs. And for example, if we have an AND gate with 3 input A, B and C, if until unless all these 3 are 1, our output will be 0. When all these 3 will be 1, our output will be 1. Similarly, if we have a 4 input OR gate, all 4 inputs, any one of these 4 inputs if is 1, our output will be 1, and if all 4 of them are 1, we'll again have a 1. Also if one is 0 and other 3 are 1, again we'll get a 1. So basically this 4 input gate will only have a 0 when all of these 4 inputs have a 0. Any one of them is 1, any 2 of them is 1, any 3 inputs of them are 1, and if 4 inputs, all 4 inputs are 1, our output will be 1. So we can have gates with multiple inputs, but is in theory. In practical life, in lab, when you perform labs or ICs, they have 2 inputs gate. We don't have multiple inputs gate, but we can design a multiple input gate, or we can represent multiple input gates by using multiple gates in the IC. This brings to the end of this lecture. Thank you.